we're going to look at some properties or laws of logs. Okay, now the properties of logs, it's really important that you understand that they are based on exponent properties. Okay, so if there's a property with logs, that same property must somehow show up with exponents. So one of the and we're just going to start with base 10 examples, but the rules apply to any base. As long as the bases are same, we can apply these rules. Now, just like with exponents, the bases have to be the same if we're going to apply any of these rules. So, how do we come up with these rules and where do these rules come from? Okay, so here's the first rule. If I have log of some number x times y, so these are factors inside a log, I can split up those factors into separate logs. Okay, I can take the log of x, log y, and the logs or exponents are added together. Okay, so this really means that the two exponents are added together. Log is an exponent, so we're adding exponents. So where does this rule come from? It comes from our multiplying exponents of the same base. We add exponents. Okay, so this is where we add logs. We're adding exponents. Well, why does this work? Well, we can try this. So notice that log of 10 to the power 5, 10 to the power 6 equals 10 to the power 11. Okay, we know that this is true. Right? We just add those exponents, okay, to get that. Now, if we say that we're adding exponents, the log rule should follow adding the logs. So if I look at these separately, so here's my rule. Here's my factors here, and I take log x and I separate it here, and this factor here would be my y. So I'm going to take the separate log of that. Okay, so I do those two logs separately. If I take the log base 10 of 5, well, that's 5. Log base 10 of 6 is 6. So instead of multiplying and adding the exponents in here, I can just take the log and add the exponents out here. Okay, and that's the same. It works out to be exactly the same. So anytime I have factors like this, now it happens to work with base 10s, but even if the numbers are not compatible bases with the log or anything like that, as long as they're factors, they can be split up in this way. Okay, so this is an example here. These are not base 10 factors at all. However, they still can be split up into separate logs. Okay, so I'm going to take log of 4 plus log of 5. So whatever the exponent that gives me 4, that's log 4, and whatever the exponent that gives me 5, that's log 5, I can add those exponents together, and that's the same exponent as if I took the exponent that gave me 20. Okay, well, let's double check this. If this is really true, the numbers should work out. Excuse me. So the log of 4, if I test this out, log 4 is equal to 0.602. Okay, so I'm going to round that to 0.602. Log 5 is 0.699. 0.699. And if I take log 20, I get 1.310. 301. And this is in fact equivalent. If I add those two numbers together, I get 0.310. So this rule works. Okay, even if we're dealing with numbers which are just really hard to understand what's happening with the powers here, we know that the power that's of these two combined factors is equivalent to the powers of those factors individually added together. And we can see it very clearly when we work with nice clean numbers, and it works in that case. It also works in this messy case down here. The second rule is the division rule. Well, if I multiply, I add, I divide, I subtract. Well, that seems reasonable. This is coming from when I divide exponents of the same base, I can subtract their exponents. Okay, so we see this in case here. 10 to the power 6 divided by 10 to the power 5, we subtract the exponents. And that's what's happening here. Okay, so let's test this in the log context. We know this works in the exponent context, so it should work in the log context, and it does. So if I divide these two factors, I get log base 10 of 1, and that's 1. I can split up this. If I have divide here, I can split up this divide. Okay, so I can do numerator minus denominator. Well, is that really true? Well, if this is logs are really what we say they are, this is an exponent, this is an exponent, we should be able to subtract those exponents. And if we work out the log separately, log base 10 of 6 is 6, log base 10 of 5 is 5. Yeah, 6 minus 1 equals the log when we did it together. Okay, so I'll show you a numerical example as well, just so that we see that it should work. So let's try some messy one with messy numbers like 3 over 8. Okay, so that should be log 3 minus log 8. Okay, so I'm going to do it with base 10. I'm going to give you some decimals, and if this is really true, this should work as well, with not just with these nice clean numbers over here, but with messy numbers. So my log 3 is equal to 0.477. Okay, so I'm going to write that in, equal to 0.477 minus log 8 is 0.903. 0.903. Okay, and then if I work out log of 3 divided by 8 all in one piece, it's going to be negative 0.426. Negative 0.426 about. If I got that decimal right, 426. Okay, so if I subtract these, okay, I'm going to get negative, I'm getting negative 0.425, but again, that would be from the rounding error. So this is essentially correct with the only error coming from rounding. So this is my rule then. If I have a division of factors inside the argument, I can subtract the logs. So how do we apply these rules? Well, if I want to write something as a single logarithm, I can put this all into one log, which is very convenient. Okay, so if I have subtraction, one way to frame this is a minus, so it's a negative exponent, so it should go in the denominator, or follow this divide rule. If it's plus, it's times, so it should end up in the numerator. Top is times, bottom is divide. Positive exponents go in the numerator, negative exponents go in the denominator. So I can rewrite this as one log. 3x, the positives all go up top, the negatives go on bottom.